Hi, welcome to the Calculus 3 lecture series. We are in the unit partial derivatives, and this is our lecture number 7. In this lecture, we're going to talk about how to find the maxima and the minima values when we are in the R3. And so it's z, it's a function of f of x, y. So how do we find the maxima and the minima values for the functions here? Okay, so let's go ahead and start. And before we introduce the formula, let's take a look, right? So let's take a look what we cannot review, what we learn in the calculus 1, and then we will see the similarities here. So in the calculus 1, so we talk about, we have a first derivative test and a second derivative test, right? So we have y equal to the f of x in the calculus 1. So we say the first derivative, we set the first derivative, and if we set the first derivative equal to 0, and this is the one we're solving for x, right? So what is this one here? We say x is what? X is the critical value. Okay, so we have two kinds of critical. So also we can find the f prime x is here, where the f prime x does not exist. Okay. So which value, then solving for x, so which value of x make f prime x is not exist? So this is another critical value we have, right? So this is how do we find the critical values in the Calc 1. So we set the first derivative equal to 0, or first derivative is not exist here. Okay, so then the next things here we talk about the f double prime x. So we set the f double prime x equal to 0. So what is after we're solving for x here? So what we are solving for? So this is the x we call it is what? We call it is the inflection point, right? So this is where the concavity change, or it could happen at f double prime x not exist. Then you solve for x. Okay, so then we also say this is the inflection point here. Okay. Okay, so now this is then also in the calculus 1, we said if f prime x greater than 0, then we know f of x is what? F of x is increasing, and also we said f prime x less than 0. So what do we say here? That we say fx is decreasing, right? So that's why, that if one increasing, one decreasing here, so we possible will have the local max or local mins there. Okay, so then we said f double prime x, right? So f double prime x, if it's greater than 0, we know that f of x is what? Concave up, right? So we said f double prime x less than 0. What do we say to f of x? We said f of x is a concave down here, right? So we said, okay, so if for the f of x is here, so that's what we have, we call this the second derivative test. If you still remember in the Calc 1, we said the second derivative test, if you put the critical points, if the f double prime x, if the critical point make the f double prime x greater than 0, because it's a concave up. So what I come out with, we come out with the local what? Local mean, right? Then if we set the x greater than 0, so it's less than 0, and then what happens here? Because it's less than 0, then because it's a concave down, so we say we have a local what? We have the local max here, right? So we know if the local max, so if the local max or local mean exists, then There has to be exist at where? Exist at a critical point, right? But the critical point doesn't mean it will give you the local max and the local means here. Okay, so that's not a necessary truth here. Okay, so that's what we have for the calculus 1. So for the calculus 2 here, we have the similar things here. So we said this is a local max, local means, right? So in the calculus 1, we say, okay, here, right? So here. So we say this area, this point here, right? So this point, we say, hey, this is a local max because it's, if you put like the small interval around it, it will, this is the highest point, and this is the local mean, right? So then also we talk about the absolute max, absolute mean. That means we need to include like the certain, certain interval. Then we include the endpoints of the interval. Then try to find the absolute max and the absolute means here. All right, so now here is the science here, right? So for the, okay, so for the calculus 3 here, okay, so how do we find the critical point? So the first thing here, we need to find the critical point. So follow the calculus 1, we said we have to have first derivative. But I have 2 variables. So I have f of x and I have what? I have f of the y's here, right? Because I have the critical point. If I have z is equal to the f of x, y's here. So it's just like in calc 1, we said the first derivative equal to 0. So I will set equal to f of x equal to 0 and y equal to 0. That's right. So now I will say that we can find the critical points here, okay? And then, or because in here we said when we find the critical points, right, is set equal to 0, that's one of the critical points, or f prime x where does not exist. So we do the same thing. So this is solving for x, or at least, one of the f of x does not exist. Oh, both they can, right? So then we said those are the critical points here, okay? And then we said the second derivative test, right? So in here we say, hey, it's a second derivative. If f double prime x greater than 0, I have local mean. F double prime x less than 0, I have local max. So in here, we also want to take a look at second derivative test. Okay, so for the second derivative test, but for the z equal to the f of x, y, I have 4 second derivatives, right? So I have fx, f of y, and the f of xy, and the f of yx. But I know if the f of x is continuous, then the f of xy equal to the f of the yx. So the second derivative test we defined in the, in the calculus 3, we say at a certain point, right? So we said this is, we call this the d. It will be equal to the f of xx ab times f of the yy ab and the minus f of xy ab, because xy and yx the same, so it's still, we said it's just the squares here. So now we have the a tables here. So that's why I'm going to show the next things here. We're going to take a look at these tables here. So this is just we talk about, right? So and if the function has a local max and the local means here, then the critical point is you set the first derivative equal to 0, because I have the partial for x, the partial for y, or at least one of the partial derivative not exist. So match perfectly, right? So the match perfectly for the calculus 1s here. So also we said if the local extrema at the z equal to f of x, y, then the AB is a critical point. okay? But the critical point that doesn't apply is it has to be local max or local mean, okay? And so in here we say a critical point, that is not the extrema, we call it is the very important, right? So we call it is the saddle point. So that means your critical point is not in the local max, it's not in the mean. So for the second derivative test here, so here is our test. The test value is f of xx times fyy minus f of xy a b greater than z, the square. So we say that d is greater than 0, okay? And then in here we say that d is greater than 0, and then the f of x is less than 0. Okay, so let's take a look here, right? So we said d has to be greater than 0, and then in here you see the like f of xx greater than 0, and the f of x less than 0 here. Okay, so let's let's don't worry about the proof of it. Let's take a look at the meaning of it, right? So when the d is greater than 0, because this number is always positive. Okay, so you have a negative signs, so it's a negative here, right? So this is, so the f of x and the yy, right? So in order for the d greater than 0, f of x and yy, they both has to be on the same sign. That's why in here we only put the f of xx greater than 0 is good, because I know the f of xx and the f of yy, they has to be on the same, right? Because if it's one is positive, if this one is positive, this one is negative, so what do you end up? The d going to end up with a negative, right? So if xx is a positive, then the yy has to be positive in order to have the d have a chance to become positives, right? So that means the xx and the xyy, they have to go the same way. So now if you take a look here, right? So if you have like some like a solid, let's see here, you have some like a solid here, right? In the, okay, so like if you have some solid here in the like the R3s here, right? So now if you take a look, what's that mean? So like the fxx greater than 0, it seems like just like if you have a, like if you have like a cross section on the x-axis and you have a cross section, like you have a plane goes through the y-axis and the x-axis, right? Because of the x-axis greater than 0, so when they go to the y-axis, the curve, the cross-section curve has to be what? If it's x-axis less than 0, that means in the x direction, it has to have a concave what? Concave down. And then for the y direction, they also have a concave down. So that's why here you're going to have what? Maxima values, right? So that's what this means here, the local max here. So that's why your xx and the yy, they has to go to the same direction. Then, that's why here, if you cut a cross section for the y, so the y has to be also is a concave down here. That means then the point here, it will be the local max. So the same ways here, like fxx greater than 0, then the fyy has to be greater than 0 here. That means both of them, if you have a solid, then when you do the like cross sections here, right? So both of them, they're going to, open upward, right? The curve, they touch it, going to open upward. So that's why they're going to have a local minimums here. Okay, so now in here, that's why I said, let's don't worry about the mathematical proof. So let's understand what that means here, right? That's why when the d is greater than 0, right? So the f of x greater than 0 will be the local minima. It's a very similar concept, just like just like what we learn in the, just like what we learn in the like Calc 1 here, right? Okay. Okay, so okay, so here, let's see here, what's the province here? And Okay, so here, well, so, okay, so I don't know what happened a while ago. I think, the internet has a little issues here, so my recording got interrupted. I hope this is not going to cause too much troubles here. Okay, so now that's why we understand why, the XX and the YY, see here, they have to have the same sign, if either positive or negative. So when the D is less than 0, so if you take a look, the D is less than 0, that means what happened here? So because like we talk about this term is a positive, then you have negative signs, negatives, right? So that means the f of xx and the f of yy. So what happens here? They have to have what? Opposite sign. Right? So they have to have opposite side. That means like if you cross section one side, like maybe your cross section like X is going to upward, and then you cross section Y, they're going downward, right? I don't know how to draw that in the 3Ds here. So that's why we call this point is what? Is the saddle point here. Okay, so like and then the next one's here, we said when the D is equal to 0 here, right? So the D equal to 0, what is the graphic meaning of that? So the D equal to 0, that means in here, okay, that means like the, fxx and the yy, they both, have the same signs here. And then you compare to the xxyy change to the xy changes here. So if they are equal 0, D equal to 0, that means the change of here and the change of here, they are at the same rate. So I really cannot decide what is this graph about. Okay, so that's why it said when the D equal to 0 is no conclusion can be made. Okay, so like I said, we don't need to understand the proof of this, but make sure we understand the meaning of it, right? So what is the D greater than 0 mean? D, like, and then why you use fxx greater than 0? Because it's D greater than 0. Fx and ffyy, they have no choice. They have to go the same directions here. All right. Okay, so now let's take a look at number 1 here. Okay, so let's see, find the critical point of f here. Okay, so let's try to do this practice here. So we know the f critical point is the first derivatives, right? So this would be negative 24 minus 6xy, right? Equal to what? Equal to 0. And the f of y is the partial derivative for y. See here, so it's 3y squared minus 3x squared equal to 0. Now I solve the system of equations, right? So I solve it, so I know from here, I say the 3y squared equal to the 3x squared. So y squared equal to x squared here, right? So I can say x equal to y over x equal to the negative y here, right? Now I substitute back to my first equation. Let's just try to test you how good is your solving system equation. So I have a negative 24 minus 6x. Now y, let's try the first conditions here, right? X equal to y here. So this is 6x and x here, right? Okay, so this one equal to 0. So I will have 6x squared equal to what? Negative 24. Oh, not possible. Okay, so no solution for this ones here. Okay, now let's try to plug in this ones. And I know x equal to the negative y, see what happened. X to negative y, this will be the negative 24. Okay, so this is negative 24 minus 6x, negative y equal to 0. Now I solve this is negative 24 plus 6x squared. I'm sorry, so this is negative x, right? So 6x squared equal to 0. So the 6x squared equal to 24. So I know x squared equal to 4. So x equal to 2 and x equal to negative 2, right? Or x equal to 2. Okay, so I know when the x equal to 2, what is my y value? Y is the negative 2. Then when x equal to negative 2, what is my y value? Y equal to 2, right? Both you substitute here. Okay, so how many critical points here I have here? So I have 2 critical points, right? So it's a 2, negative 2, and the negative 2, and the 2's here, right? Now let's try to find the critical extrema, right? Okay, so now let's double derivative fxx. So that this one will be negative 6y, good. Then the f of yy is here, so this will be 6y, right? F of yy is 6y, and then the f of xy, okay, so xy is take derivative of y here, it will be negative what? Negative 6x. Okay, then let's take a look at the b. This is how do we decide, like the second derivative test, fxx, so it's next 6y times 6y minus, right, negative 6x to the square. Okay, so this will be negative 36y squared minus 36x squared. So here. Okay, so now let's take a look at D. Now I put in my critical point 2 and the negative 2. So what I'm having here, this is a negative 288, and the D and negative 2, negative 2 and 2, is negative 288 here. Okay, so let's back to here. So this is less than 0. So that means one go up and one go down here, right? So what are those points here if the less than 0? So I know both here, 2 and the negative 2, and the negative 2 and the 2 are what type of the point? A saddle point. Right? So we know there are no local extrema. All right. Okay, so now let's take a look here. The second problem here is also kind of like want to ask to, kind of use our definition. So let's say to classify each critical points here, right? Okay, so let's do a tables here. So this will make it a little easier. Okay, so this is the point, right? So we'll do a similar table. Let's do here, instead of do a separate one, we can just extend this table. Okay, so we say, okay, let's just extend this table, and then we can have a D, right? Okay, so the D value, okay, so this is X, so the D value will be Fx times Fy, so it's A times 2 minus negative 4 to the square. So it's 16. Well, so this is equal to 0. Okay, Q is 1 times 9, right? XX times 9 minus 2 to the what? Square here. So it's 9, so this is 5. 0 4 here is 0 4 here is will be okay, fx, so it's a negative 6 times 3 minus 1 square, so it's a negative 19. Then the s here is a negative 2 times negative 5 minus 9 minus 3 square is 9, right? So what here is 1. Okay, so according to, we say, if D is greater than 0, so if this one here is equal to 0, so we can determine We need more information, can determine, right? Okay, now both Q and S, right? Both Q and S, they are greater than 0. So they are greater than 0, then we know the local extrema exists. But these ones here, look here, right? Like I told you before, the XX and XY, they have to have the same sign. So they both, the f of x, so it's open upward. So what I have here, I have a what? Local mean, correct? And so the same ways here, so S here, this is, greater than 0 also. Take a look here, right? Both of them, they have the same signs here. That means both of them open downward. If open downward, what's that mean? I have a local what? Local max here. Okay, so now in here, take a look here, like we talked before. Hey, one is this sign, one is this sign, right? So they have opposite sign. That means one open upward, one open downward. So what the point we say here? This is the saddle point. All right. All right. So let's see is the how to find the local maxima and the local minima. Okay, so now let's go kind of do a quick review in the calculus 1. How do we find absolute max and means here? So we say in the calculus 1, right? So that means if I have a function go like this, right? All right, so then I have areas here. This is A and the B's here. So I know my function. So this is f of x here. Then my domain is from the A to B. So it has to be in a closed interval. So how do I find the, the absolute max and the absolute means, right? So the first thing is here, you find the critical values here, right? So you substitute the critical value. Okay, so how do you find the critical value? F prime x equal to 0, right? So that you find in the use the F prime x to find the critical value. Right, so like say we have a critical value C. Of course, you can have C1, C2s, right? Then we just compare, you substitute the C to the functions, right? So find this value, then you substitute the two endpoint A and F of the B, right? So because these ones here, right, that's the endpoint here. So then you compare which one is the largest one, which one is the smallest one, right? Then you can define the absolute value. So it's the absolute max or the absolute mean. So for these situations here, right, this point is local max, but at the same time, is also is absolute max because we are defining in this close intervals here. So in the calculus 1, how to find the absolute max and the absolute mean, it's pretty easy, right? So what do we do here? We just substitute the endpoint. Now in the calculus 3, let's take a look. It might not be that easy here. Okay, so let's take a look at here. We say absolute max here, right? So that means in here, that means this number greater than everything in the what? In the domain. It depends how do you define it, okay? So that's why we call this the, absolute max and absolute means here, right? And then, so that's why basically, how do you find the absolute extrema? So you find on a closed and bounded set and compare to the critical points, just like we did in the Calc 1, but the Calc 1 is pretty simple. You just need to plug in the two endpoints of your intervals here. Okay, so let's take a look. Let's say the number 3. Let's say, does the absolute extrema exist for the f of x squared plus y with domain x from the 0 to 2 and y from the 0 to 3? Does it exist? Yes. Right? Why? because I know that f of xy is x squared plus y squared. So f of xy is a what function? It's a continuous functions, right? Okay, so this is a continuous function. And your domain D is what? Is both closed and bounded. Okay, that's what we mean closed and bounded, right? Because in here, your domain right now is in the R2. So it's from the 0 to 2, 0 to 3, right? So this is your domains here. So it's a closed shape and it's bounded by the, you have the boundaries here, right? So this is bounded here and it is closed. Okay, so yes, it is. Okay, now the real test to find it is not that easy. That's why in the later chapters, so we're going to introduce, we call this line integrations here, try to simplify those things here. Okay, so let's take a look, right? How do we find the extrema values here? Okay, let's take a look at this example. I have a f of x equal to 10 minus x squared minus 2y squared plus 2x plus ay, and here is the domain. All right, wow, okay, that's fine. Looks pretty complicated. I want to find the absolute max and the absolute min. All right, so let's do a step by step. First things, just like in the calc 1, I need to find what critical value. Okay, so the critical value, okay, partial derivative f of x is negative 2x plus 2. Right, set equal to 0. This is pretty easy. X equal to what? 1. F of the partial derivative y, so this is negative 4y plus 8 equal to 0. This one's easy. Y equal to what? Y equal to 2. That's the only critical point, right? That's pretty good. So this is our only critical point. There's no other one. So this is 1 and what? 1 and 2. Okay, so I can substitute the critical points here, but the problems here is I have these boundaries, right? Okay, so this boundary, that's just like in the calculus 1, the critical point taking care of the point inside. But now I have these boundaries here. So that means for each boundary, just like in the calc 1, we need to substitute the 2 endpoints. Now we need to do is take a look at these 3 boundaries here. Okay, let's take a look at the boundary number 1s here, right? So here for these lines here, the green ones here. All right, okay, so for this is we call this line 1 because we need to consider all the boundaries, right? So the line 1, okay, so line 1, this is the one on the x-axis, right? So the one I highlighted in the greens here. So what is here? So y equal to 0, right? What is my x value? X is from the 0 to what? 0 to 4, right? Okay, so now the y equal to 0, then my f of xy is equal to what? My f of xy will be the negative x squared plus 2x plus 10, right? Because all the y cancels, right? So I have a 10 minus x squared plus 2x. Okay, so now, well, this is back to what? This is back to the, calc 1. So I can say, okay, then the derivative is here, right? So this is, I can say this is the x y equal to 0. So the derivative here, it will be negative 2x plus 2, right? Equal to 0. X equal to what? X equal to 1, right? So this is my critical point. Okay, so now just like in the, in the calc 1, I substitute 1. So I substitute 1, so it's 10 plus 12. So this is 11. Then also in calc 1, what we did? We substitute what? We substituted the 2 endpoint, right? So this will be the endpoint 0, 0. So what is here is 10. Then we substitute the another endpoint is 4, 0. So 4, 0 is negative 16 plus 8 plus 10. So what we have here, we have, so let's see here. So it's negative 16 plus 8 plus 10. Oh, okay, it's 2, right? Okay, so now at this line, the green line, where is my, this is what? This is my max, right? This is my maxima, and this is what? This is my minimum here. Okay, now let's go ahead to do the next line. This is my yellow lines here. Okay, let's go to the next page. And okay, so let's go to the next page. My next lines here, this is a line 2, the yellow lines, right? This is on the y-axis, right? So that means x equal to 0, then y is from the 0 to 4, right? So then let's take a look at my f of 0y, because x equal to 0, xy. So what is my f of xy here? X equal to 0. So I have a negative 2y squared plus ay plus 10. Okay, wow, that's pretty good. We're back to what? We're back to the calculus 1 again, so we can find the derivatives here. So let's say to find the critical point 0y. So this is negative 4y plus 8 equal to 0. So I can get y equal to what? Y equal to 2, right? Okay, so then I also, now let's just plug in to see what the largest value we have. So y equal to 2, so 0, 2, I plug in back to my function. So what I have here, so this is the 2, 2 is negative 8 plus 16, so it's 18. That's right. Okay, so okay, so I have the here, so y equal to 2, make sure we did it right. So this is 2 times 4 plus 16 plus 10. So this one is 18. All right. Okay, so then I have the other end here. So the end here is 0, 0, right? So remember that x-axis here, so you need to plug in the end point like we did in the calc 1s here. So this one here is 0, 0, is 10. Now I need to plug in the 0, 4. The 0, 4 is here, 16. So it's negative 32 plus 32 plus what? Plus 10 here. So this is 10. Okay, so now here, this is the max, both, this is the max here. These two are the same, so they both is the minimum here. Okay, so that's our second line. Okay, so now let's take a look at the third line. So let's see, the third line is these blue lines here, right? So that's the third boundaries here. Let's take a look. So the third line is here. Okay, so this is line 3. So this is the one. Okay, so this is the lines with x plus y equal to 4, the lines here. All right, so this is a line. So since x plus y equal to 4, so what is the y? Y is equal to the 4 minus x here. Now I substitute to the xy, I substitute to the y equal to the 4 minus x, so it's x 4 minus x. Then you substitute to the functions, right? So the function is 10 minus x squared minus 2y squared. So what is y squared? Is minus x squared to 4 plus 2x plus ay. So what is y here? Is 4 minus x. Oh boy. Okay, foiled it and combined. So you will get this is 10 plus 10x and minus 3x squared. Okay, so now it's back to the calculus 1. Okay, so now I can take the derivatives, right? So I need to find the critical point. So the critical point is 10 minus 6x, and that is set equal to 0. So x equal to what? 5/3 here. Okay, so x equal to the 5/3. Then take a look here. You know, the two endpoint we already did, right? 4, 0 and 0, 4. So we don't need to worry about that. Okay, so now let's try to put all this summary together. So here, right? Then we see, okay, so what happens here? So the xy is here. Okay, so let's take a look at the line 1, 1, 2, right? So the 1, 2, right? So okay, x equal to 1, 2 here. Hey, so, oh, and did we get the 1, 2 here? Okay, so 1, 2, let me see, where is the 1, 2? Okay, so we did, okay, so we did a line 1, line 2, and we forgot to do is find the only critical point, F12. That means what is the value of F12 here? Okay, the F12, you substitute back to the f of xy, and I'm getting the 19th here, right? All the other, the red one is the one we did on the boundaries here. Okay, so now let's try to find now. Okay, so on the line 1, I have, okay, on the line 1, I have like 1, 0, 4, 0. Right now on the line 2 here, I have a 0, 2, and I have a 0, 4. Okay, so then we have here, this is the max on line 1. And what is the max values here? Okay, so this is 11. 4, 0, this is the minima on line 1 and line 3, right? And line 3. So this one is give us 2. 0, 2, this is the max value on line 2. And we got is 18. And 0, 4, this is the minimum value on the line 2. And we have here is what is 10 here. Okay, and then we have the next point here. So here, the 0, 4, this is also the number on the line 3. Then we also have this number 5/3. Then the y value is 7/3. That's on the line 3, right? So this is the maximum number on the line 3. Okay, and so then the maximum number on the line 3 is 18.33. All right, so we got this one is x equal to the 5, 3. So we say y equal to the 7/3. So that's basically on the line 3. If you plug in, I skipped these steps here, 7/3 into the function, you will get a 18.33 here. Then we also last one, this is our critical point. So this is the critical point. And what you have here, so it's 19 here. Okay, so now this is just like we consider all the values on the boundary and on the critical point. Oh, here, this is the largest one. So what is this one here? This one we call that this is absolute what? Max, right? Then let's take a look at what is the smallest value. Then the smallest values here we see is what? Is 2. Okay, so the smallest value, this is the absolute what? min at the 4 zeros, right? Okay, and then the 19 at where? 19 at the critical point. So that's what happened to our maxima value, absolute max and absolute min. That means we need to consider, you know, all the close boundary. Like you can see this boundary, you know, like you can see this boundary is just a triangle. It's already very tedious. That is why when we go to the chapter 16, we're going to introduce a different concept about the line integrations. And then this type of the problem will become a lot easier, right? So if I have the close boundaries here, so how do I do the integration and how do I find the values will become a lot easier. Okay, so now let's take a look at another applications here. Okay, so this ones here is also, you know, later we'll have a different method can show you and simplify it. So let's say show that among all the rectangular parallel piped with a volume 1 cubic meter, then the one with the smallest surface area is a cube. Okay, so what do they mean here? So I have a parallel, so it's rectangular parallel pipe. So basically it's telling you it's just a what? It's just a, you know, it's just a rectangular box here, right? So I have this is X, Y, and the Z, okay? So let's say we are given, right? So here we said, hey, I want the volume of this is equal to 1. So X times Y times Z is equal to what? It's 1. And then we said the one with the smallest surface area, okay? So I know the surface area is equal to what? Is equal to the 2xy plus 2xz and the plus the 2yz here, okay? And so we said that whatever the smallest surface area is a cube. That means this is, I call this a surface, right? So if the minimum value of the S, right, then apply the X equal to Y equal to Z equal to 1 here. Okay, so let's take a look and see we be able to show that or not, okay? So I know here, right? So the given is X, Y, Z equal to 1. So I can replace it. So I know the Z is equal to 1 over X, Y, right? Okay, so now I can rewrite my surface area is equal to the 2xy plus 2xz. So what is z? Is 1 over xy. Then plus 2yz. What is z? Is 2xy, right? So my surface area is 2xy plus 2 over y plus 2 over x, right? Okay, now let me set the partial derivative, find the critical point. So the partial for x, this will be 2y, this term disappear, minus 2 to the x squared, right? So I want this one equal to 0. And what that means here, so that means my y is going to be equal to 1 over x squared, right? Okay, now I'm doing the partial for y's here. The partial for y, this will be equal to the 2x minus 2 the y squared, all right? And this one has to be equal to what? Equal to 0, right? So that means 2x, so I can from here, I can get x is equal to what? 1 over, okay, 1 over y to the square. So now I have y equal to 1 over x squared and x equal to 1 over y squared here. So if you replace it, okay, so if you solve this equation, so y is equal to what here? X is 1 over the square, right? So it's y squared to the square. All right. So what you have here? So you have y equal to the y what? Y force. Okay, so now let's try to solve this. It's y equal to the y force. That means y and the 1 minus y cube is equal to 0. So I know y equal to 0 or y equal to 1. And I know the what? I know the y cannot be equal to 0 because y equal to 0, there's no box here. So y has to be equal to 1. And so if y equal to 1 here, then the z is equal to 1 over xy. And so the y equal to 1. So then if you y1 here, you put it back here, then you can apply x equal to 1. So what is z here? Is 1 times 1 is 1. So that's how do I prove x equal to 1, y equal to 1, and the z equal to 1, right? So those are these ones here, we know the side of this boxes here has to be what? Has to be 1 in order to get the minimum values here. All right. And so that's it for the, for these sections here. So that's how do we try to find the value by using the partial derivative, and also try to, try to use the partial derivative and try to the critical points and the second derivative test to try to see the maxima and the minima values here. All right, and so for here, that's it, and I hope that you get a good understanding about how to find the maxima, local minima, and the absolute max, absolute min, right, in the R3 situations here. All right, so the methodology is aligned with the calculus 1. It's just we add the extra, the variables here. Okay, that's it. I hope that you guys get a good understanding about this topic, and so you'll be able to find the maxima and the minima here. All right, that's it. Okay, have a good day.